A moving charge in a magnetic field 2. The diagram at right shows the path of an electron of charge E, mass m, and velocity v, 1 before it enters a region of uniform magnetic field of magnitude v, as well as 2 for a short time after it enters the uniform field as it curves around in a path of radius r. In our figure here, we have an electron approaching from the bottom of the page. It enters a region of uniform magnetic field and then travels in this curved path. In the figure, use symbols to represent the magnetic field. We need to figure out in what direction does the magnetic field act. And the way we figure that out is we realize that anything that's traveling in a circular path has to have a force on it that is directed towards the center of the circle. So at that point right there, there's going to be a magnetic force. You learned this in mechanics, didn't you? Anytime something is traveling in a curved path, there has to be a net force towards the center of the path. If we use our pat-pat right-hand rule, how do we need to orient our hand such that the electron's velocity is towards the top of the page, and the force, which is the pat-pat part, right there at that instant, is going to be towards the right. So you see my fingers? They're pointing into the page. There is a uniform magnetic field, and into the page we represent with X's. Sometimes we put a circle around the X's. And I should put X's uniformly here, but there's a lot of other stuff in the diagram, and I don't want to do that. Those X's represent the direction of the magnetic field. Letter B. Draw a vector starting at point P that shows the direction of the net force on the electron at point P. Okay, well, similar to what we just did, it's always going to be toward the center, isn't it? That is, that FB is a centripetal force, isn't it? In fact, magnetic force on a moving charge is always a centripetal force. Derive an expression for the magnitude of the B field based on the given variables. First of all, whenever we have forces, it's probably a good idea to use Newton's second law. So let's use that as a starting point. F net is equal to the mass of the object times its acceleration. Here we have an object that is moving in a curved path, and we learned in mechanics that that centripetal acceleration is given by the expression v squared divided by the radius of the motion, which in this case is capital R. And then the net force is going to be the magnetic force. And the magnetic force has what magnitude? Q, V, B, and then since it's a cross product, the sign of theta. What's theta with regard to the direction of V and the direction of B? You can see that theta is always 90 degrees. And if theta is always 90 degrees, then the sign is 1. What I'm seeing here, let's rewrite this. Q, V, B is equal to m v squared over r. It looks to me like one of the v's is going to cancel like that. We know what q is, and actually, because of this problem, it's not given as q, it's given as e. So we should really change that to e. So let's go ahead and do that. That q, I'm going to write it as e. And we want an expression for the magnitude of the B field. I think we need to divide both sides by E, and let's see what that gives us. M times V divided by R divided by E. We were told at the beginning that we know what M is, we know what R is, we know what V is, and we know what E is. There you go. That will be the magnitude of the magnetic field for this case. For a charge q having mass m and moving at a velocity v through constant gravitational, electric, and magnetic fields, the equation to determine the net force on the charge due to these fields is basically there's a gravitational force component, there is an electric force component, and then there is a magnetic force component. And these don't all necessarily point in the same direction. Gravitational force on the mass of the charge, there's the electric force on the charge, there's the magnetic force on the charge. Again, we have to take these into account vectorially. Letter B, let's finish with why is it that in the real world the gravitational contribution to the net force on a moving charge is usually ignored? That's because the electric force and the magnetic force portions are typically many orders of magnitude larger than the gravitational part.